Thanks, Jumar, for the introduction. Today, I want to tell you about ZOE. And as you heard, this is a joint work with Bell Labs, Cambridge, and Intel Research. Before I begin, though, I want to tell you about this painting to the left. This is a painting by Pietro della Cortana. He was a Roman painter in the 1650s, and what it depicts is this child, as you see at the bottom there, being guided by a guardian angel. And the connection to our work is that we want to investigate in this work, what would it take for a self-contained, tiny, wearable sensing device to provide somewhat of the same experience of having your own guardian angel. Now the sort of characteristics we need to have is a device that is able to observe us throughout the course of your day, right? It's not just when I'm in the gym, but it's when I'm driving my car, it's when I'm interacting with colleagues. The other thing it has to do is it has to interact with me in a reasonable, natural way. So this angel here, this child is able to ask it questions for guidance. It's not analyzing graphs, right? So that question we ask ourselves, is this type of experience even somewhat feasible in a prototype device? And in some of the limitations that you find in wearable systems today, like the one I wear every day, this Fitbit device, is that they have this tunnel vision of our lives. It's a huge impediment, because what this device sees in me is just how much exercise am I doing throughout the course of my day. You could argue that I need to exercise more, but the fact is I do many other things during the course of my day. I interact with people, I get stressed, I go to different places, and these are all types of environments and types of sensory information that I want my device to observe. The second failure of wearables today is the way they provide us with our information, right? So Fitbit, you name it, they have this notion in terms of quantified self, where the idea is that I guess you come home every night and you study these graphs, right? So at the top right-hand corner is this really fine-grained, fascinating information about sleep patterns that an application can collect about you. But if you think about sort of the next sort of billion people outside of the early adopters that are a quantified selfers, people like grandmas, very busy people, they're going to want to have more natural interactions with your data if they're going to benefit from it. So again, this is another failure of wearables that this type of device called ZOE is really trying to address. So with those two examples in mind, here is the type of sensing and interaction we want to have with ZOE. I've highlighted here two main types of sort of workload the device tries to provide. In the top right-hand corner, you see a small picture of the device. I'll get to that later. The first thing I'm highlighting is this ability to sense a diverse range of everyday activities. So in the later part of this talk, I'll be telling you how ZOE is able to sense when I'm stressed. It knows when I'm doing physical activity. It also quantifies the types of environments I'm entering and measures them. The second primary thing that ZOE tries to do is provide this information not in terms of graphs, although we do provide these sort of conventional visualizations as well, but what we really want to try to do and add to the wearable experience is a very natural dialogue-based interaction. So the idea here is that when I'm alone by myself and I'm maybe driving to work or I'm by my computer, I know there's a device by me that I could answer sort of simple questions that's able to respond, and I'm able in this way to learn about myself in a very sort of lightweight fashion. I'm not sort of changing the way I live my life, right? So the examples I've got here is you can ask ZOE, am I stressed more than last week? And start to correct these sort of behavioral biases you might have. You might think you're very stressed, but ZOE is able to tell you, well, actually this week has actually been relatively normal for you, right? And if you look at these two things as workloads, they have sort of really strong challenges associated with them. So on the sensing side, we have multiple types of sensing pipelines having to be executed. Some of these operations, such as the dialogue interaction, are time sensitive, right? So if a person asks ZOE a question that takes 10 minutes to answer, it's not very natural. And of course, we have this sort of classic problem here where you have to observe these workload challenges with subject to energy, because after all, what we're trying to do is provide a wearable, self-contained experience here. What we decided to do in this work was to address this problem by using sort of the rapidly emerging, fascinating types of hardware that are available. So one example, and actually the heart of the prototype we built, is the Intel Edison. We worked with Intel closely on this work. They're able to provide us a lot of support in trying to access different parts of this chip. It's amazing what it provides you. It provides you, in a very small form factor, a 500 megahertz CPU that's almost Pentium class. Also inside it is a lower power chip. They call it the Quark. It runs at 100 megahertz. It also has 100 gigabytes of RAM, and again, this is a small, tiny form factor. Intel, of course, is not the only one. I saw recently Samsung wants to get into the game, providing similar types of system-on-chip engines. And if you look at other folks like Qualcomm and NVIDIA, it's remarkable what they offer you. I mean, if you just look at the LG G smartwatch, inside that is I think it's a 2-core CPU and a DSP. What's telling though is that in recent teardowns they looked at how it's being used. The DSP is completely not used and only one of the cores is being used. So again, this ZOE prototype is really getting towards how do we want to build wearables that have these really extreme types of workloads and addressing these, not necessarily by going to the cloud, although we wouldn't rule that out. We want to see how you can address these by having heterogeneous types of computation locally available. So now for ZOE. On this left-hand side you see the prototype. The heart again is the Edison, but underneath it is a daughter board. It offers 3 tiers of computation. There's at the top level, there's the Atom CPU that we want to use sparingly. It's supported by the Quark MCU. And then we added a third component, another chip running at 48 megahertz. And the lower part here of the architecture, you can see how these different components, particularly the Intel board, provides us with, again, these 2 types of computation, as well as a Wi-Fi radio that's important for doing place sensing. And then this daughter board that runs underneath, we attach a variety of additional sensors that the Edison lacks, as well as a third CPU for helping support the workload. Right, now there's a lot happening in the system. What I've decided to do is focus on 2 main modules that I think are most interesting. The first I want to speak about is the sensing module. What we've done is we've been studying basically a lot of the work that this community and other communities such as Ubicom, Census and MobiSys have done over the years, and we wanted to identify how could we support all of these inferences going on at once. So literally what you see on the left-hand side is everything that ZOE is able to provide us. So it runs from, let me go through one by one. So we have transportation mode that's telling us whether I'm driving a car or not. We have physical activity. These are just the classic activities everyone wants to try to infer, things like walking, running, and being stationary. Then we have conversation analysis. Actually was a system for presenting this type of analysis was done by Junhua and back in MobiSys 2013. There's stress detection. This is just a binary classifier that's looking at audio data, saying, am I stressed or not? There's place detection, which uses also audio, which uses Wi-Fi to detect when you enter a place and when you repeatedly enter the same place. There's also place context work, which seeks to use the audio to understand the type of, basically the ambient environment. Is it dominated by music? Is it dominated by conversation? Is it loud? Is it medium? Is it soft? And finally, voicing and audio context. Now that classifier is just trying to tell, do I hear a lot of voicing going on, basically conversation or not? Or is there music or other types of sound classes present? And when we looked at this work, a lot of the times you see these types of workloads being studied, often on a smartphone, and often when they're simultaneously trying to provide 1 or 2, perhaps in the outlier 3 of these. What we did was we came up, let me first describe a little bit about one of them, just so you got a sense of what's going on here. I chose an example, stress sense. This is work that was presented at Ubicom. Basically, they're looking at the audio spectrum. There are telltale signs of when people are stressed. For example, pitch, rate of speech. They build a Gaussian mixture model that's able to identify being in a stressed or non-stressed period. And if I just map this, what I've done is, this is the overall design of our sensing module, and I've mapped that in purple and showing you how stress sense is realized. Now in the sensing module, all of the prior types of inferences I was describing are supported. What we found was there was an awful lot of redundancy in the types of features that need to be extracted. Often there's not much you can do about the classifiers at the bottom layer, but by using data, by reusing features and especially reusing the data being collected from the raw sensors and some of the pre-processing, this single module is able to offer all those inferences I've described earlier. The trick to making this energy efficient though is partitioning all these algorithms across different hierarchies of computational units. So let me show you what we did. At the top right-hand key, you see the Atom CPU, Quark, and this IT MCU. They're color-coded. Where black shows you, where red is showing you what's the workload that we provided to this ITE MCU. In blue, I show you what we assigned to the Quark. Now the thing is that basically the ITE is providing a lot of the inertial sensor type of inferences. The Quark is performing a lot of the early stages of the audio pipelines, and then in black we have the Atom CPU performing this work. And it's then that way that we're able to drive the energy cost down dramatically. Now finally, because we want to support a dialogue interaction, not only do we record just the raw inferences, we also associate them in terms of a database, in terms of the time and locations where they are occurring, so that later dialogue interactions can support this type of workload. We also do some simple transformations from, say, raw inferences of step counting into calories. The goal of, and other things like carbon footprints, the goal of this is not to be really accurate with those type of transformations, but just to sort of realize more natural types of information being presented to the user. The second subsystem of ZOE that I want to talk about is the dialogue subsystem. And highlighted in blue is components we reuse from the sensing module. They also run on the Quark. Now what happens is that ZOE is constantly listening for a keyword, namely its name. So how I interact with it is I say ZOE and then I give it a phrase. Because that is the key entry point into the pipeline of the dialogue subsystem, we invested a lot of our computation on providing a high fidelity of accuracy for recognizing the word ZOE or not. So we used actually a DNN, a deep neural network, that runs on ZOE to recognize just a binary, not ZOE, ZOE. It's 3 layers, it's 128 nodes. It provides us with state-of-the-art recognition of this key stage. Where we compromise somewhat is on the speech recognition accuracy. We just don't have the computation to provide a sort of a state-of-the-art word recognition system. So we're both using an HMM, GMM-based speech recognizer, and we constrain the vocabulary down to 300 words. Now, this stage, once you recognize the words, is fed into a dialogue reasoning system. Now, we use a template-based approach. This is not what they use in Siri and Cortana, because we don't have that sort of computation available to us, but it's a well-understood approach in the dialogue community. What it does is that you define a series of phrases, things such as how much. You have different classes of words, such as activities, duration, and you assign them in terms of a series of templates. From these templates, the system can recognize literally thousands of different queries, but it is a constrained way of interacting with the system. And what I showed here is a couple of examples. You can ask ZOE, when did I finish jogging today? And it's able to understand this because there's a template that understands, okay, what does it mean for when to be sort of composed with, say, jogging? What does it mean for today? Also, within this template system, it's relatively easy to associate the different types of questions that can be asked with ways of responding. It doesn't respond in very natural ways, it responds in a fairly mechanical way, but again, this is a first prototype. In the rest of the talk, what I want to do is show you 2 key results, and then I'll be summing up. The first is a key important question of how good is the battery life? The second one is, just how accurate and responsive are the the dialogue and the sensing subsystems. So to answer that first question, essentially it lasts for 30 hours. This is based on a prototype that has a 1500 milliamp battery, a milliamp hour battery. The battery takes up most of the weight, The weight of the system is about 50, 55 grams, depending on the case. The way we derive this number is with a trace-based measurement where we input into the system a series of data, accelerometer data, gyroscope data, and so on, and we make assumptions about the different types of interactions a person is going to have throughout the day. So we assume there'll be 8 hours in a normal day of silence, because folks sleep for 8 hours. Typically, also, we've found from prior studies that people have around 4.5 hours of speech interaction. And what I'm showing you here is a graph where we have the battery capacity being used up.
Represents our ZOE prototype. For 24 hours of data, we use 78% of the battery life, which implies the 30 hours I mentioned. Now the next result I want to show you is how accurate our ability to understand the dialogue queries coming in. We had 11 speakers. We randomly generated 25 commands for each of them based on the potential sort of complete workload that is possible given the template-based system. And what we find is we have 80% accuracy. Now, if you break that down into the error rate by word, you see we're getting about 87% accuracy on our words. What we find though is the keywords are, because of a query is composed of a number of different words, as long as we get a sufficient number of those words correctly, we're able to design for the right template. What I also show here is a table showing the benefit of the custom dictionary that we're using compared to other types of dictionaries we find out there. So Sphinx is a well-known speech recognition open source system. They have a variety of different dictionary sizes, and we're comparing the delay in processing when you have a constrained dictionary that we use, the 300 versus say 6,000, or the complete dictionary of 133,000 words. And you can see that when we have our constrained dictionary, we have this real-time factor of 0.23, which basically means that we can process one second of data within 0.23 of the second and maintain our real-time requirement. The final result I want to show you is the accuracy of our sensing module. So to create that sensing module, we had to make a few compromises with the techniques that we're using while remaining true to the core principles that these other papers have identified. What we did is in many cases, these papers, authors of these papers gave us their raw original data, so we repeated their experiments in many cases. So for example, let's see, for place context, right, this second from the bottom. This is work done by Glue's group at Microsoft. They gave us the raw data of 168 locations for which they inferred the different types of context going on, is it a very noisy environment, how much speech is going, and so on, and then we replayed that data through our system to come up with an accuracy rate. We find in each case that our accuracy rates are relatively comparable to the ones reported in the papers. So basically the result is that our sensing module is approximately the same as the types of things in the original work. So just to conclude, I wanted to sort of highlight where we're going next. What I haven't mentioned so far is that the Edison device, initially we used a lot of the closed components of this device, and that's why we worked with Intel. But just last week they released many of these things to the public. So Edgar and I were able to do some quick back-of-the-envelope calculations based on the actual released version of what we find. We think we can actually increase the battery life of ZOE dramatically, so perhaps up to 3 days. This graph is the exact same graph I showed earlier with respect to the battery life, but the purple line being shown is the amount of speech per day with this released version of the quark that's inside the Edison. Basically the quark turns out to be much more capable than we first thought, as they were able to push more components onto it, we're able to lower that curve. And so now if you're willing to have a battery of 1500 milliamp hours, you can have a battery lifetime of around 3 days. Potentially we have to verify this result, we just did this quickly. Also, very importantly, we haven't been able to do user trials yet, so we will need to verify just what sort of user experience people have when they have these sort of dialogue, spontaneous interactions, and really see what that really means for their experience of using a wearable. What we think is a very interesting direction to explore, and the key part of this work is showing it's actually feasible by building wearables in this way. So to conclude, today I've spoken about ZOE, what it's really sort of driving towards is the types of wearable systems that can give you the sort of guardian angel-like type experience, where they're with you throughout the course of the day. They're able to observe you no matter what you're doing, and you're able to interact with them in a very natural way. And the way that we realized the system was to take a very hardware and software combination sort of approach to the problem, where we want to understand how we could support this sort of workload by assigning different types of actual sensing algorithms to different computational units in a small form factor to support a fairly unique workload. And so with that, I will take questions.